Greetings to all of you. So here we are back with another important topic of kinematics physics. So in our last video we have discussed about the mechanics and three of its types, three of its frontiers, which were statics, dynamics and kinematics. And we discussed about the motion and rest and the motion phenomena and the types of the motion and what does it mean to be a unit mass or a particle. So these were all about the last video. So in this particular video we are going to discuss about the frame of reference. So frame of reference is of great concern when we discuss about the kinematics or the classical mechanics thing. So frame of reference plays an important and crucial type of role in our measurements. So for a practical example, let me say that there are three persons, two of them are sitting in a train, and the third person is standing on the platform watching both of them. So if we ask the person one about the person two's motion or rest, he will say that person two is in rest. But if we ask person three about person two, he will say that person two is moving. So who is telling the truth about person two? So this is the beauty of physics, that both of them are true. The major thing that impacts, that affects, is the frame of reference. That with what reference we are taking our measurements. So there is another example. So let's say there is a car that is moving with a velocity of let me say 80 kilometer per hour with respect to the surface of the earth. So if an observer is standing on earth beside the road and he watches the car moving with 80 kilometer per hour, so this is all about the frame of reference, which is the earth. Now let's suppose there is moon, or let me say sun, and a person hypothetically is sitting on sun, watches all of this scenario, all about this car. Then what will be the estimated velocity of that car? So as we know that the earth itself moves 30 kilometer per hour angular velocity with respect to the sun. So the 80 kilometer hour frame of reference earth's velocity is different from the observation from sun. So this is how the frame of reference takes part. So there are two major types of the frame of references. So first one is the inertial, and the second one is the non-inertial. So when we talk about inertia or inertial frame of reference, inertia is sometimes regarded as mass. So this is all concerned about the Newtonian mechanics and the laws of the Newton. So for easy to understand, let me say that the inertial frame or the frame of reference in which the Newton's law holds. And what are the Newton's law? A statement of a Newton's law is that if a body is in rest, it will stays in rest unless some external field changes its position. And if a body is moving, it will keep moving unless some external field interacts or interrupts the motion. So in any of the frame of reference in which both of these conditions are fulfilled, or we can say there is a more generalized form that there is no acceleration. Sometimes some of the teachers use this analogy rather than the upper two, but ultimately all of them are interconnected. No acceleration means that they are moving with a constant velocity which is not changing. That's why acceleration is zero. Net acceleration change is zero. So this is the inertial frame of reference, and the vice versa of it, that in which Newton's law does not hold, are non-inertial frames. So it is a bit difficult for you guys to imagine that how does a frame of reference be non-inertial, because this is a practical kind of thing, and all of us get different examples in our daily life about the inertial frame of reference, considering the air resistance and the friction of the surface along with the study. But what does it mean by a non-inertial frame when no external field is interacting but still the body is moving? How is it possible? So here's an example of that. So let's suppose we have a truck, I must say, and a ball is hanging in this truck. And at the time when he starts its velocity from 0 to some value, let me say x meter per second, at just the time it starts traveling, the ball, it don't have any direct connection with the external circuit, which is a truck, but still it get pushed back. So this is the contradiction about our imagination, that our body is in rest and it should stay in rest unless some external field acts, but here we see that a body is in rest and the frame of reference, or we can say the truck, is moving and it pushes the object back. So this is a kind of non-inertial frame. Another example is of free fall motion in a lift, let's say. So if we have a ball and then the rope get destroyed and we get a free fall motion, that the object is moving downward but the ball keep moving towards upward. So this is about the frame of reference. This is a brief, this is not the brief kind of history. We will discuss the frame of reference in our relativity topics or the classical mechanics thing. So this was the first phase of our discussion of today's lecture, which is the frame of reference, and the second one is of the coordinate system. So coordinate system is also a crucial part to understand all the measurements, all the things, all the motions and all the rest as well. So what does it mean by a coordinate system? So as the word refers, coordinate, that it coordinates something to something else. So let me say we have a butterfly in our room. Let's suppose that the room in which you are sitting or laying this time, you watch as a butterfly flying in middle of the air, and you have to specify the location of that butterfly, let me say P. So what should you do? So you have to distinguish, you have to design some kind of frame of reference that might be consciously or subconsciously, but you have to tell the position of it with respect to something. So we have three, this is the Cartesian coordinate system, by the way. There are three type of most popular coordinate system. First one is the Cartesian, second one is the that was a polar coordinate system, spherical polar, and the third one is the cylindrical. We use x, y, z axis in Cartesian. We uses z and theta in polar coordinate system, and we use z, theta and r, theta and z in our cylindrical system. So these are of less importance here, because we are planning to design another playlist concerning about the classical physics topic. So we will discuss them and their conversion and about the Fourier transformations, all about that in a later discussion. So till that, we are here to discuss the Cartesian coordinate system, which is the simplest among all of them. So we were on a point, we have to specify the location of a butterfly. So let's we say that butterfly is here and you are here. So this is the uh, origin, this is the coordinate point, this is the origin, ultimate origin, from where you start taking the measurements. So to reach point P, this you have to travel this much of x. You have to travel this much of z. Let me name it x1. This much of, let me say, z1, and this much. If you imagine it in three-dimensional, it will get more benefits. We have another video, we have another diagram which might be helpful to you. So you can see that to reach point this, we have to travel this much of x, this much of z, and this much of y to reach this position. So in three dimensional, the imagination is far from the other perspectives. So this is the x1, this is the y1, and this should be the z1 to reach. So x1, y1, and z1 are the coordinate point, are the address points of this point. So this is the coordinate system. So mostly we discuss about the three-dimensional coordinate system, which is x, y, z, but we can shift that to 2 and 1 dimensional motion. So this gives another classification of motions which might be of three-dimensional, two-dimensional, or one-dimensional motion. So in three-dimensional motion are x1, y1, z1. All of these parameters will be converted, will be altered. In our two-dimensional motion, some of the teachers do not write the three coordinates as well in the, but we are writing it. So the x1 will change to x2, y1 will change to y2, but z1 does not change. So two of the dimensions get changed. So that's why the motion is two-dimensional. In our three, in this one dimension, only one of the dimension, either x, y, or z, will be changed, and the other ones will stay that same. So this is the classification of motion on the basis of the axis. So to imagine this, we can say that we will draw that pattern again, because in our last diagram some of things get too messy. So here is a point. So let me say to reach this we have to travel this, this, and this. Now it sounds better. So this is the x, this is the y, and this is the z. So this is the z1, and this is the x1, and this is the y1 to reach this P point, which is x1, y1, z1. And if this butterfly goes from this to this position, let me see, so we have to travel more. So this much of z, which is z2, this much of x, which is x2, and this much of y, which is y2. So this new position, let me say P2, is x2, y2, and z2. So this is the three-dimensional motion. In a two-dimension, we only draw two dimensions to simplify the calculation. This is the x and y, and here is a point. So to reach this we have to travel x1 and y1, and if this position get displaced to this P2, we have to travel this much of x and this much of y. So the new position P2 will be x2 and y2. And in a one-dimensional motion, let me say this is only from x-axis. Our body is firstly here, and then after some time it goes to there. So the P1 is x1 and P2 is x2. All the other x's are available here, but these x's do not get changed, so that's why they are of lesser importance. This is all about our discussion today. In the next lecture, we will discuss different kind of analogies and terminologies associated with the kinematics, like acceleration, displacement, velocity, and that kind of all the things we will cover in the next lecture. Till that, stay vibing, keep studying.